there's a cutie trying to learn some math with us. Hello.
Say it again.
Like
She did say hi, but I was muted.
That's cute. All right, let me pull this up. Okay, some people are still. Hi, Sean. Hi, Andy. Hi, Delaney. Hi, everyone. Hi, Lori and Lori's child, whose name I've forgotten.
It's Aria, but
Aria. Okay. Hi, Aria. Oh, so cute.
Nice background.
Yeah, right. You know, the thing is, this is the art project that I was the head of that went to Burning Man in 2018. And actually, there's me, right? That's me. The picture. But yeah, it was so good. We just found out that Burning Man's canceled for this year, and I was feeling kind of sad. So I thought I would just put my little picture up so I could look at it and cheer me up a little bit. So yeah, so Burning Man may be canceled, but I'm still doing weird stuff. This is what I did this weekend. So I have to turn the volume down because check it out. It's not quite done. It took me forever. But yes, that's a toilet seat. Look, the heat gun is changing the colors. So mood ring toilet seat, homemade by yours truly. It exists. I'm gonna have to do, this was like, I don't know, 20 layers or more of this stupid ink trying to spray. I actually bought a, what's it called? An airbrush, like a tiny airbrush for makeup. Who uses an airbrush for makeup? I don't know, but I bought it and then it keeps getting clogged. These are like thermochroic crystals that are getting blown out. And if you just bump it a little bit, it scratches it off. So I need to put a bunch of layers on and then spray some clear coat first. But I tell you what, it's not going to be long before you can find out what mood your butt is in just by going to collab. So yeah, I'll invite you all over for a sit down when it's safe to do so. Okay, yeah, so that's happening. I'm still finding ways to just embarrass all of you, basically. So that'll keep up. Does anybody do anything fun this weekend? That's what I did this weekend. Seriously, I watched people do the silk painting class, and I just sprayed ink with my makeup spray brush on a toilet seat. That was my weekend. Can anyone top that? I mean, seriously, just about everybody can top that, right? No. No? Okay. Well, all right.
That's pretty awesome. So I can't really top that. So.
All right. Well, I tell you what, and if any of you want one, I know how to do it. Come on down. I'll give you the sprayer. Got a couple hours to just, it can be yours. You can totally do this. All right. Let me share some. I'm so glad you have your screens on. Just makes me so happy. You have no idea to see your faces. I miss you so much in person. And it's this is not a substitute, I know, but it's just still nice. Okay, I'm going to share my screen because, as usual, I have some announcements. And plus, that's what we do in class. Where is it? Okay, there it is. Okay, some stuff. So these are just reminders. You already know this, but if you want, you can. I realize redo it just seems weird, but I couldn't think of another way to say it. So if you want, you can redo a homework assignment and try to go from a 0 to a 1 on it. But you only have to April 27th to do it because the graders are sort of doing this extra grading. I think they're probably doing it for free, honestly. I don't think they're going to be able to squeeze it in. So, but then we need to give them enough time to fit it into their own schedules. Do you know what I mean? So you really got to get it in by the 27th, and they're committed to getting it back to you by May 7th. I realize that's a while, but they're still doing the other grading on top of it, so and this one they won't be commenting on, right? They'll just be giving scores, and that's coming up. Send it by email to that address rather than Gradescope. Also, course project, if you want to do it, it's optional. You don't have to do it. You can still get an A without it. if you want to, I mean, maybe you want to just because you want to look into some new thing that's interesting. Maybe you want to because you want to bump your score from a B to a B plus or something like that. Like those are perfectly good reasons to do a course project. That's going to be due May 18th. That's our last final, or at least in our class's last final. I don't think there's another final after that or whatever. And at 11 p.m. And but you know, if you wait till May 17th, you're not going to be able to do something good enough to cover the threshold. So like, don't even bother. But I would like to know what you're doing by May 4th. I would like to sort of have given you my approval, because one thing that I think neither of us wants is for you to, you know, spend some time on a course project, and then for me to say, well, that's not enough to get credit. Do you know what I mean? Like, you need to know this in advance. Right. So kind of me saying, I'm thinking about looking into this, and I could say, whoa, that's way too much. That's like half a semester's worth of material. No. Or I could say, well, maybe if you add a little bit of this, that's going to be substantial enough. Or do you know what I mean? And I can sort of help you with that. Also, I can maybe help add fun things to it. So if you want to do it, meet with me by May 4th. Tell me what you're thinking, and I will, and we'll get something going. Somebody asked me to update the grades on Google Drive. I was going to wait to do it till the 7th, but you know, why not? So it's updated last night. I'll update it on the 7th, and then that'll be the end of it. And the official evaluations are out. So you did a great job of being reflective, and when I asked for the sort of course progress report and suggestions and so on, and I think I learned a lot. And I also think, you know, it was just nice to read the things that you read, and that was great. None of that though goes like to the university, right? That was just for me to learn something. So you may feel like, well, I already wrote it, and that's okay too. But if you want to write it and have it be part of the record, then could you write it again? Or if you've changed your mind, I mean, write the new thing, right? But I mean, yeah. So sorry about having two things in one class, but there it is. Those are out, and I hope you'll do them. I'm supposed to encourage you to do them, and I want you to do them. Like, go ahead and do the evaluations. That's your right, and that's your way to communicate with your professor what they need, what they should keep doing, and what they should try to work on. Okay, so those are announcements. Now that I've said all that, ooh, let me see if the chat. Let me open the chat window up. Are there any questions about any of this? No? All right, so let's talk about, oh, so here's what we're gonna do for the rest of our time together. We're gonna talk about rings and fields. We're gonna talk about section 19 integral domains, and then that's it. We could do more stuff, but I thought about going a little bit further into this first homomorphism theorem stuff. I mean, that's the really important stuff, I think. But it's kind of too big of a can of worms for the extra time that we have left over. And it's not something that you're going to benefit from if we just ram it in there. So I decided to not do that. I think what I'm going to do, we're going to have some extra time. I think we might have an extra day. We might even have an extra class period and a half. And what I want to do with that time is I'll just bring more examples to work on. I'll just pick problems out of the book or pick problems out of some other book, and we'll do some proofs together. And if you want, you can go into breakout rooms, you can work on homework together, or you can, you know, work on practice problems together. I'll come up with practice problems for you to do. And so it'll be a little bit, it won't be sort of new material as much as it'll be trying to reinforce the previous material. And then that's it. So we'll have like sort of a calm, plus you got stuff going on, right? You got exams coming up, possibly have a course project you're going to do, right? So I think it's a good time for me to pull back a little more. I asked the last class if they thought that would be too boring, and one of the students was like, yeah. So sorry, I hope you won't find it too boring. I'll try to spice it up. I mean, I'll pick problems that are fun, and hopefully that'll make a difference. Okay. Somebody asked about the exam in the last class, so maybe I'll just say something about it. I've sort of said it before, I guess, but I'll say it again. There's gonna be 4 problems. Oh yeah, he asked, I didn't say this before, he asked sort of what you should expect out of the problems. So for the written exam, written quizzes so far, what I've tried to do is to have the first one be, a little bit lighter weight and more computational, and the second one a little bit heavier weight and more proofy. And I'm limited to 20 minutes. So I haven't really been able to ask anything too substantial because of that sort of time crunch. We have more time on the final. So I have the freedom to ask something very, very, very slightly more substantial. I probably won't have one of the four be the lighter weight computation ones. Probably it'll be more like the second problem, or maybe just the tiniest little bit harder than the second problem. But you'll have 2 hours for it. So you'll have half hour per problem. And also, so on a regular final, if you do one problem and you don't do 3 of the other ones, then you've only got 25% max. But that's not the case here, right? If you do one problem and you don't do the other ones, then you have one extra problem to add to possibly kick out a lower score, right? So even if you just do one problem in 2 hours, that can help you. So and if you don't do any problems, it doesn't hurt you. Like if you've got other fish to fry, which I'm sure we all do, and you're like happy enough with your grade, that's cool. And just go do your other stuff. And you don't need to take it. There's no personal shame in not doing it. There's no anything like that. It's just an opportunity for you to show up some extra points. Okay, now that's all the comments I have to make. But I'm ready for questions. Let me just give it another second. Does anybody think they're going to be taking the final? Nope, nope.
I'm a little bit confused. Is the final not? I feel like you've probably gone over this. Is it not like mandatory?
Optional. Yeah, finals
Oh.
optional. Yeah, so the number of points that you need, that like you need certain number of E's, certain number of whatever, blah, blah, blah. All that is achievable with just the 14 assignments we've already had. But let's suppose you feel like, oh, if I just had one more E, I could get an A in the class. I want to try again. Then you can take the final. And if you get an E on one of those, I'll sort of use that one.
Okay.
Yeah.
I for sure was planning on taking it.
Okay, yay. Okay. So Jordan will be there. Me and Jordan. It's kicking it. Okay.
When do we have to decide by?
If you tell me by our last class period, which is what, the 6th or something? I don't know. If you tell me by our last class period, that's fine. Okay. Anyone else? Okay, let's talk about rings and fields. I can't even remember. I think all we did last time. So we stopped at a different place than the other class, but I think we wrote the definition of a ring down, and that was it. Is that right?
You gave us a warning.
Oh, what did I warn you about? Oh, closure, I bet.
Yes.
Yeah, okay, yeah. So warning, binary operation means closure. I'm just rewriting, this is just the definition. I just want us to see it again. So, but it's from the end of last time. So this is sort of a recall. What does it mean to have a ring? Well, okay, so when you have a group, you had a set and a single binary operation, and binary operation means closed. You have to take from G, cross G into G, so the output has to be an element of the original set. And then you had all those properties, dissociative, you had existence of identity, you had inverses, et cetera. Bug flew in my eye today, and I don't know that all the bug bits are out yet. It's kind of gross. So so that's what it meant to be a group. And but a lot of the things that the purpose of abstract algebra is to abstract from the algebra that we've been doing, in high school or for the algebra that we all do all the time. And so what are the properties that we need to do that kind of algebra? Well, some of from the first day of class, I gave you this sort of linear equation that was like x plus 3 equals 5. And we realized, oh gosh, we need the associative law. We need additive, we need the identity, we need inverses, we need all that stuff to solve. That's a group. Well, I could also say, 2x plus 3 equals 5, and you could be, because that's two operations. There's multiplication and addition. So let's say, well, what kind of rules do we need to solve those sorts of things? Okay, so so lots of sets have two operations on them. We're going to talk about rings that have two operations that have certain properties. I just want to remind you that R means ring. That R doesn't mean real numbers. So R is just any old set. And that plus, that could be like a *1 and a *2. It's a first operation and a second operation. And that first operation, we're going to call plus, and the second operation, we're going to call multiplication. But it could be anything, it could be composition of functions and something else. It could be whatever. You just need two binary operations. These things might be matrices. These things might be functions. These things might be, polynomials, or, like they could be anything. Okay, and then what do you need? Well, the first operation has to form an abelian group. So a group that has a commutative property. And then all you get out of the second operation is, closure, because it's an operation, associative law, and distributes over the first operation. If you have all that stuff, it's called a ring. And so, oh yeah, let me just remind you, here's the section is called rings and fields. Section 18, rings and fields. Okay, so let's think of some examples. Well, your book has a lot of examples. There's so many examples of rings, but let me just sort of add a couple of them. Well, the integers with ordinary addition and ordinary multiplication, that's a ring. Well, we already know that the integers with plus is a group. That's something we've been dealing with for a long time. Multiplication is associative on the integers. We know the distributive law. Okay, so that works. It also works for the reals. It also works for the rationals. It also works for the complex numbers. So okay, here's sort of a meta ring, M sub n of R, where R is any ring. What does M sub n mean?
Isn't that the set of all n by n matrices with I guess entries from R?
Yeah, that's exactly right. And if you had invertible, then it would be GL and R. But you're right. You corrected yourself, and it's just the n by n matrices where the entries come out of this ring R. Okay, so that forms a ring. We already know how to add and multiply matrices. And you can't multiply all matrices, right? You can't multiply a 2 by 3 matrix by a 5 by 17 matrix, but these are all n by n, so they're going to match up to multiply. So multiplication is associative and the distributive law works, so that's cool. What else? Oops. Functions from the reals to the reals. So if that's our set F with addition and multiplication, that's a ring. Also Zn with addition, addition mod n, I should say, and multiplication mod n. It's kind of easy to be a ring. You don't need that much more. There's this thing called Z adjoin 2, Z adjoin square root of 2. What does this mean? Well, it's all the sort of linear combinations of 1 and square root of 2. So it's all the things that look like a plus b times square root of 2. So it's sort of like, what would you get? What kind of what would you get? What kind of ring would you get if you start with the integers, already a ring, and then you just threw in one more guy, just throw in the square root of 2? How does that mix it up? Well, closure means that you're going to need to be able to add any real number plus a square root of 2, but you also have to add the square root of 2 to itself, so you get, you know, any. So really all these sort of linear combinations are going to have to be in there. So all these things are rings, and many, 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 many more. Okay. So here's where things are interesting, fun, and confusing. So now that we have 2 operations, we sort of doubled our complication, right? Because having 2 operations, there's, you know, you have to think about the identity for one and the identity for the other. You have to think, how do those operations play with each other, right? And so we already have the distributive law works. That's one of the ways that they play with each other. Here's some more. So, so the question is, how do the binary operations, you know, combine together? And the answer is going to be in this theorem. And this theorem is going to seem super obvious because this is what you've been doing your entire life. It's just, it's going to feel second nature. And I want you to try to divorce yourself that for a minute, because it's second nature only in the number systems that you're familiar with. I mean, that's fine, but it's not, you don't know for sure that it's going to be true for any other weirdo number system. What I want to show is that these things we're about to write down are true as long as you have the properties of a ring. It's going to work. So it'll be true for n by n matrices. It'll be true for, you know, z adjoined 2. It'll be true for functions. It'll be true for all these things. As long as you have a ring, these statements will be true. So here's a theorem. Here they are. So first, so okay, so as far as a ring, and 0 is the additive identity. Where am I? So then for all A, B in the reals, not in the reals, I'm sorry, for all A, B in the ring, I'm going to say that a bunch of times and I'll regret it. 3 things are true. So first of all, if you multiply A times 0, think for a minute. This is weird. 0 isn't the number 0 necessarily. It's the thing that represents the additive identity. So if we have n by n matrices, it's an n by n matrix with a bunch of zeros in it. But it could be I mean, it just has to be entries are in a ring. So I could get weird and I could just say, what if I have 3 by 3 matrices where every entry is a 2 by 2 matrix? I can do that, right? And then the 2 by 2 matrix has entries in z adjoined 2, right? So all these things, 0 isn't necessarily just the number 0. It's the thing that's the additive identity. So I know what happens when I add it to stuff, nothing. But what happens when I multiply it? So I'm taking the additive identity and I'm using the other operation on it. Okay, so that's what's weird about this. And when I do, I better get the additive identity back. That's the first statement of theorem. You want a number system to act that way. I think you would feel disappointed, or you wouldn't have that much faith in doing your math in it if it didn't have that property. Okay, so that's one. Also, here's A times the additive inverse of B is the same thing as the additive inverse of AB. And that's the same thing as the additive inverse, as the additive inverse of A times B. I'm sorry, AB should be A times B, right? 3, the additive inverse of A times the additive inverse of B is the same thing as A times B. These all seem reasonable, but also a little bit surprising because it's combining additive inverse, additive identity with multiplication. Okay. All right, so to prove it, first thing we have to do is, let's do it in yellow, abandon your preconceived notions of what has to be true and instead just use the ring properties. So that's step one. Take a step back from stuff that you already know about other number systems. So what's the proof? Let's do three things. So first of all, okay, so I need to prove that a times 0 is 0. So this is kind of cute, and this is kind of why I like algebra, but this may be why you hate it. I mean, it's very cute and tidy, and you might think, oh, who thought of this? But you got to admit, it's kind of fun to look at. So what if I don't know what a times 0 is, but I can still add it to itself. See, what do I have for a ring? I don't have much. I've got the group, sure, with addition. I've got associative law, and I've got the distributive law. That's all I have really is the distributive law. That's the thing that combines plus and times. So I have to lean on that distributive law to get anywhere. So that's a good reason to just, like, if I add these two together, then I can use the distributive law. So I can say that's the same thing as a times 0 plus 0 by distributive law instead of by left distributive law. And 0 plus 0 is 0 because 0 is the additive identity. Zero is the additive identity, so I can say that's a times 0 plus a 0. Okay, look, I've got a times 0 plus a times 0 equals a times 0 plus 0. What do you think I'm going to do?
A times 0 equals 0.
Yeah, what property are you using there, Giacomo?
Left cancellation.
Yeah, left cancellation. That's right. Because R is a group with addition. So whatever these green objects are, who cares? The point is I've got one of them plus another one equals the first one plus something else. And so I can left cancel. So by left cancellation, okay, so a times 0 is 0, and all we've used is the distributive law, the definition of the identity, and left cancellation. I don't know what I just said, but I meant to say a times 0 is 0. And then, the same thing goes for 0 times a, so similar proof for. Okay, let me just pause for a second and see if in case there's any questions about that, to give you just a chance to catch up. Oh yeah, Jordan.
I don't know if I have a question so much as it's kind of a comment, but it's just, it's kind of hard to believe because it makes sense, I think, when you're thinking about like 0 in terms of just like, when you think of it in terms of just like numbers and stuff, but then thinking that this is true for a case where your field, the underlying set, is like the set of 3 by 3 matrices, and then each one has like a 2 by 2 matrix as an entry.
Yeah.
It's like, this is not obvious at all, but it is funny the way that the algebra makes it seem just like so crystal clear, like just a few operations. But it's really, really weird to think that that's generally true for lots of different objects.
Yeah, I agree. I mean, it feels, to me, it feels a little bit magical. Like all you've done is you've made up two operations. And they could be totally different. And it's just this distributive law that's driving this whole thing. You know, otherwise you could feel like, well, they're completely unrelated. They don't have anything to do with the plus and multiplication that we know that the objects aren't even the same. Yeah, so it feels like kind of magical, I think. Okay, so that's problem one. Problem two, what about A times minus B? Okay, so where should I start? Let me think about this for a second. Okay, so what does this thing mean? This is the additive identity of the element AB, of the element A times B. That's the meaning of that symbol. In other words, if I add that thing to A times B, I get the additive identity. Let me just write that down. So note that the symbol negative of A times B, that is the additive identity, the unique. Oh, sorry, I meant additive inverse of AB. So it's the unique thing that when you add it to AB, you get 0. If I show that something else added to AB gives 0, then it has to be this thing, because additive inverses are unique. So that's what we're going to do. We're going to show that that silver thing added to AB gives 0. So it has to be the additive inverse of AB. So it has to be negative A times B. Okay, so that's the strategy. So we will show that, let's say, A times minus B added to AB gives 0. Then A times minus B will have to equal minus A times B. Normally in a proof, you wouldn't necessarily write all this stuff, but I think this way of thinking may feel new to some of you. And so I wanted you to sort of look at the outline behind the proof. Okay, so that's what we're going to do. Let's do it. So if I do A times the additive inverse of B and I add that to AB, well, what can I do here?
Could you do the distributive laws again?
Yeah, good. That's exactly what we want to do. We want to do the distributive law. Really, that's all we have, right? We've got the ring, we've got the distributive law. So let's lean on that again. So that's going to be A times the additive inverse of B plus B. By the distributive law. Well, the additive inverse of B, if I add that to B, I get the additive identity, right? That's the meaning of additive inverse. So that means I get A times 0, since minus B is the additive inverse. And what's A times 0?
0.
0.
Right, because we just proved that in part 1. Okay. So that means A times the additive inverse of B is the additive identity. I keep saying that, additive inverse of AB. But this one is the unique one, so they have to be the same. And then a similar proof shows the other side. Okay, other questions about this one? Okay, this third one's kind of fun. What are we trying to show? Negative A times negative B equals positive A times positive B. Negative and positive is kind of a weird thing to say, right? Because if I have a matrix, is that negative or positive? It doesn't even make sense. I don't know why I said the word positive. That was insanity. It's just A and B, or the additive inverses of A and B. Okay. So, well, if I want to show that these two are equal, one way that I could do that is I could show that, I know the additive inverse of this is written like this. If I showed that this was the additive inverse, if I showed that this plus this was 0, then this would be the additive inverse of this, therefore these would have to be equal. That's the goal. So we're going to show that. So I'll give you that little outline again. We will show that minus A times minus B added to the additive inverse of AB is 0. And then since additive inverses are unique, we'd have minus A times minus B is the same thing with AB. Okay, so that's the strategy. Does this strategy make sense? Yeah, okay, nice. All right, well, let's do it then. So the additive inverse of A times the additive inverse of B plus the additive inverse of AB. Oops, why did I do that? Well, let's see. Let's deal with this left side. So if I use property 2, and I leave this like as one object, then this is the same thing as the left-hand side is going to be the additive inverse of A dot negative B. And then so this is by theorem part 2. Then if I use theorem part 2 again and pull the minus out for the B, then I've got a minus of A times B. By theorem 2 again. Okay, what do I have? We have this guy and its additive inverse. Right? This whole thing is the additive inverse of this whole thing because it's this thing, additive inverse. So so this sum, it has to be 0. Since the negative of the additive inverse of A dot B is the additive inverse of That's the notation for the additive inverse. Okay. So that means that this thing in green, negative A times negative B, is the additive inverse of the additive inverse of A dot B. But so is A dot B. Since they're unique, they better be the same. Okay, so all these things that you've used as a kid growing up, this is why they're true, because you've been dealing with rings, and rings have these properties. You didn't even realize you didn't know why they were true, probably. Okay. All right, so that's that. I'm gonna give some more definitions, but let me just pause for a moment, reflect, see if there's any questions about the theorem. Okay, no, let's, okay, so what's the first thing that you do? Of course, if you're a mathematician and you start defining a new type of object, then you say to yourself, well, when do we consider these objects the same? What does it mean for them to be the same? So you know I'm going to define homomorphism and isomorphism, right? I mean, that's the obvious next step. So here's our definition. So let's say that R and R prime are rings, and let's just give just to be super clear, let's give the operations name. So let R with plus and times and R prime with plus prime and times prime, let these be two rings. In a map, B from R to R prime is a homomorphism. Some people will call it a ring homomorphism. For all A and B in the domain. Well, okay, so a homomorphism for a group, the idea there was that operation on for one group works the same way as the operation for the other group. What's going on here? I've just got two operations. So the homomorphism is going to be, first operation on one group acts the same as first operation on the other group, and also second operation on one group acts the same as second operation on the other group. So we just got two pieces to write, but I hope that they're going to feel, I hope this is going to feel like exactly what I should write to you. So let's see. If I take A and B and I add them using the operation in R, I could take A and B and add them using the operation in R and then send it over with B, or I could just send the components over and add them with the operation in R prime. And you should get the same thing. So it's the same thing as if I send these components over one at a time, and then I add them with plus prime. Similarly for multiplication. If I do A times B and then apply phi to it to take it over into R prime, I should get the same thing that I get as if I take A and B over by themselves, and then I multiply them together using the multiplication operation in R. So that's what it means to have a homomorphism. So it's a group homomorphism and more, right? Both operations have what you'd call the homomorphic property. And I hope this won't be a surprise here. An isomorphism is just like it was for groups. You have the homomorphism property, and then you also have to have a bijection between the elements. So same thing's true here. So an isomorphism. Oops. phi from R to R prime is a homomorphism, which is 1-to-1 non-two. Here's kind of a cool fact. Cool or disturbing, depending on how you see mathematics. An isomorphism of groups does not extend to an isomorphism of rings. Like if you have some two groups and your favorite isomorphism between them, and then you realize actually you can make them rings. That doesn't mean that that thing that was an isomorphism of the groups turns out to be an isomorphism for the new operation that you're adding. So there are isomorphisms of groups that don't extend to isomorphism of the rings. So for example, let's think of the map from the multiples of 2 to the multiples of 3. So a multiple of 2 looks like 2 times n for some integer. And let's just take that to 3 times n. Is that a group homomorphism? Well, let's see. So if I have 2 elements in 2z, so let x, y be in 2z, then being at multiples of the integers, that means then there are an n and an m in the integers such that x equals 2n and y equals 2m. Okay, so phi of x plus y is phi of 2n plus 2m. That's the same thing as 2 times n plus m. And what does phi do to that? That takes it to 3 times n plus m. That's 3n plus 3m, and I know that's phi of x. Well, let me do the extra step. I know that that's phi of 2n plus phi of 2m, and so I know that's x plus y. Oh, sorry. I know that's phi of x plus y. Okay. So it is a group homomorphism. Why isn't it a ring homomorphism? Let's just try some values and see if they blow it or not. I mean, you know, if we try some values and it works, okay, doesn't tell us anything. But if we try some values and it doesn't work, then we know we've blown it. And let's just see if we can find a counterexample. Okay, so let's just try 4 and 6, I guess. So let x equals 4, y equals 6, and both of those are in 2z. Then phi of x times y is phi of 4 times 6. That's phi of 24. And how do we make phi work? Well, we write it as 2 times something. And we respond with 3 times something. And what is phi of x times phi of y? So that's going to be phi of 4 times, I sure hope this doesn't work, times phi of 6. So phi of 4 is going to be phi of, that's 2 times 2. And phi of 6 is going to be 2 times 3. So this is going to be, so what does, so phi takes 2 times something and turns it into 3 times something. So this is going to be 3 times 2 here. And then this is going to be a 3 times 3 here. And that's 6 times 9, which isn't 36. Okay, didn't work. Okay. So just because you have a group homomorphism doesn't mean it's going to be a ring homomorphism. Right. Okay, so that's rings. You could spend a lot of time talking about rings. So, for example, so you mean you could spend your entire life studying algebra easily and not cover it all. When I was an undergraduate, I had 4 semesters of abstract algebra, and we spent a lot of it, maybe at least a full semester, probably a full semester and a half, talking about rings and fields. There's a lot to say. I'm not saying just telling you these definitions is enough. I'm saying that that's kind of what we have in terms of time. And now at least if somebody in your future says, oh yeah, this is a ring, you'd be like, oh yeah, I remember, that's kind of like a group. It's got some other properties. I can look it up. Okay, so that's rings. And now let's talk about fields. Okay, so I hope this has occurred to you. So we have this other binary operation. And I hope you've been thinking, I wonder if it's a group with that binary operation too. I wonder if it satisfies any of those properties. Does it have, is there an identity? Is there a multiplicative identity or not? Does anybody have a multiplicative inverse? Do they all have multiplicative inverses? These are the sort of questions to ask. And here's one thing, here's a fact. Some rings have multiplicative identities and some don't. So for example, the integers, and some don't. For example, the even integers. You know, for the integer, the multiplicative identity is 1. You know, for the even integers, the multiplicative identity is 1, but that's not in the even integers. So the even integers don't have a multiplicative identity. Okay, so here's some definitions. I'm trying to think of what the right analogy is, but maybe one of you can tell me the best analogy for this. But this whole business we have so many, you know, there's so many different properties, right? There's the existence of an inverse, there's existence of an identity, there's for both the plus and the times, and that's commutativity or not, and there's so many different combinations. And you know, somebody's thought up some name for all of these freaking different combinations. And generally speaking, you know, there's only some of them that people mostly study, and some other like fringe elements study the other ones. But you know, there's even things called a monoid and a groupoid. And I think they're, you know, I forget, the monoid has, both of those things have all the properties of a group, except one of them is missing. And then, you know, what kinds of number systems does fits that? And well, okay, so I'm about to take rings and add all sorts of different properties onto them and tell you the different names when they have these different properties. Okay, so if you have a ring and multiplication is commutative, you already know that addition is commutative. That's part of being a ring. Okay, but if you have a ring and multiplication is commutative, it's called, not surprisingly, a commutative ring. So a ring in which multiplication is commutative is a commutative ring. Okay, a ring that has a multiplicative identity is called a ring with unity. So we have to, we have to be careful about identities, right? I'm saying multiplicative identity or additive identity. You could also say, wow, how did I spell multiplicative? That's just crazy. Okay, I was supposed to write. So we've got these two identities, possibly. We definitely have an additive identity. We might have a multiplicative identity. Usually the additive identity they call the identity, and the multiplicative identity they call unity. So so we call this a ring with unity. And unity is like a 1. And the multiplicative identity is called the unity. What's a ring with unity? Can anyone think of an example?
Would just the integers be one?
Yeah, the integers would be 1. Lots of things that we know are, we're used to having a multiplicative identity. It's weirder for us when we don't, right? So the integers, yes, with plus and the rationals, yes, and the reals, yes, and the complex, yes, and integers mod 12, yes. Those things have a multiplicative identity. Okay, that's fine. So here's some more definitions. Also, matrices, n by n, n by n matrices, that works, with real coefficients, something like that, because, we know the multiplicative identity. We know what that is, right? It's got 1s down the diagonal. Okay, so that's also a ring with unity. So let's suppose R is a ring with unity. One, that's not the same thing as 0. I don't want you to look at this and as the number 1 and the number 0 and think that, a math professor writing 1 does not equal 0 is just insanity. Of course it doesn't equal 0 if you're thinking of those as the numbers, but we're not supposed to think of them as the numbers. We're supposed to think of them as the 1 represents the unity. It might be the identity matrix for all you know. The 0 represents the additive identity. Okay, so this is the symbol representing the multiplicative identity. And this is the symbol representing the additive identity. Okay, so if you're ring and you've got these two identities and they're not the same, here's some more definitions. Let's see, we're at 2, let's do 3. An element of R that has a multiplicative inverse in R is called. Okay, so some of you read that article. And they talked about some items having multiplicative inverses and some not. What was the name they used in that article? What was the name of the conjecture from the article? Nobody remembers?
I'm just gonna throw out a random guess here. Was it invariant or was that something else?
Invariance was talked about in the article, but that wasn't the conjecture. So the conjecture was called the unit conjecture. And so we call the elements that have multiplicative inverses, those are called units. So it's called a unit. So this should hint at you that maybe, maybe there are some elements of a ring that are units and other ones that aren't units. Maybe they're not, not everybody's a unit. Okay, so, but sometimes they are. So if every non-zero element of R, 0 can never be a unit, right? Because 0 times anything is 0. You can never do 0 times something and get 1. So if everything else, so if every non-zero element of R is a unit, what does that mean? Everybody has a multiplicative inverse. You can divide, right? Multiplying by the multiplicative inverse is sort of the same as dividing by something. You can divide. It's called a division ring. If you also have commutativity, then you've got a field. So a field is a commutative division ring. So think about some examples. What are the integers? So we already know that's a ring. What does it count? So it's it's a commutative ring, sure. It has a unity. Unity is the integer 1. Is it a division ring?
No, because there aren't inverses.
Yeah, no, because a lot of things don't have inverses. Yeah, right. So not a division ring. What are the units? Are there any?
-1.
Yeah, good. -1 and also 1. 1 may seem cheesy, but you may feel like, oh, well, that's the unity. But still, it has the property that if you multiply it by another number, specifically 1, you get the identity out, you get the unity out. Okay, so so it has 2 units and then nothing else. Okay, so it's definitely not a field because it's not even a division ring. Okay, what about Z12? Here's what I want you to do. I'm going to have you do a little classwork. So I'm going to just tell you right now that Z12 isn't a field. And so what I want you to do is find the units of Z12 and then make a conjecture about how they relate to 12. And then make a conjecture about what it's going to take for Z sub something to be a field. So meaning division ring, I mean commutative we already have, but so division ring, everybody has a multiplicative inverse. Okay, so I'm going to open some breakout rooms, let you chat with each other for a little bit. We'll do like 10 minutes and then I'll call you back for just the last couple of minutes to talk about it. Oh gosh, all these unassigned. Okay.
low key, the only question was like, is
Dr.
there an
Hoppus.
equivalence class between these two? Just did not turn that one in because I had no idea. But hey, Dr. Hoffus, we I think we have finished number
First
number
one.
1. We want
Okay.
to say that the only unit is the 1 because the reciprocal of 1 would be the only one that's in the unit, or sorry, in the set here.
I don't think you should think the word reciprocal. Just because that word sort of makes sense in the integers and the reals, but maybe that's not really, well, I guess you could say the word reciprocal, but multiplicative inverses don't have to look like 1 over something. That's sort of what I'm trying to say. So there's actually more.
Okay, I see.
All right, I'll check with them. So try some of the values and think about it. Okay.
Sweet. Okay. Jordan, I think that.
Oh, the multiplicative ID is unity, so I guess that'd be equal to like 1.
Okay.
I take a picture of it. Oh wait.
Hi, Dr. Hoffus.
Hello.
Your
Oh,
office.
hello. Just stopped in to see if there's any questions you had.
I don't think so. We got 1, 5, 7, and 11 as units so far.
Good. Yeah. Okay.
All right.
Okay.
We did have a question. Could you have 2 different, because for these ones we'd have to square, like we'd do 5 squared would be 25, and then that would end up being 1 mod 12. But if is there ever a possibility where the units, there's 2 units multiplied together that end up?
Oh yeah.
Okay.
Yeah. It's kind of weird this time that 7 squared is 49, and that's 1 more than a multiple of 12. But you don't have to be your own multiplicative inverse.
Okay. Gotcha.
Yeah. Oh yeah, that makes sense.
Just checking in. Does anyone have questions?
I think so.
So have you found out what the units are?
It'd be everything where you can multiply it, but well, we're still going through, but like it'd have to be something where when you multiply it together, it equals like 12n plus 1, basically.
Okay. All right. I'll give you some more time to do that. Maybe a couple more minutes and I'll bring everybody back.
Alrighty.
Hey, just want to stop in. Have you found the units?
I think so.
What do you think they are?
1, 5, 7, and 11.
Yeah, good. Okay. Do you have any conjectures?
We think that, so those are all relatively prime to 12. So we think that if n is prime, then everything will be relatively prime to it. And
Yeah. So good. Okay. Nice. Okay. I'll call everybody back in like 1 minute and then we'll all talk together. Okay.
Cool.
Dr. Hoppus,
Yeah.
do you mind going up to the examples you just gave? Or the ones right above the classwork. Because there's the part, it says like commutative ring with unity, and then you can't see what it says after that. It says equal.
Create a ring with unity. unity.
equal to 1.
Yeah.
Gotcha. Thank you.
All right, so let's see, let's talk about number 1, units of Z12. So a lot of you came up with 1, and one group said that 1's the only one because it's the only one with a reciprocal that's an integer. And so that's a good answer for the integers. Well, 1 and -1, it's a good answer for the integers. But for Z12, there are more. So 1 works. What are some other ones that work?
5 and 7 and 11.
5 and 7 and 11. Yeah, that's right. So 5 times 5 is 25. That's equivalent to 1 mod 24. I mean, 1 mod 12. 7 times 7 is 49, which is 48 plus 1. So multiple 12 plus 1, etc. Okay, so these are the units. And how does that relate to 12? Well, those are the only numbers that are relatively prime to 12, right? 2 and 3 and 4 and 6 and 8, those will show up. So these numbers are relatively prime to 12. So what's our conjecture? What would n have to be so that everybody has a unit? What would n, in order to be a field, everybody, so that everybody is a unit, so that everybody has a multiplicative inverse.
If n is prime.
Yeah, if n's prime, then everything is relatively prime to it, right? So if n is prime, then Zn is a field. And usually they'll write ZP just to sort of emphasize that, you know, P doesn't have to be prime, but usually they put that just sort of as a like a thought, as a reminder or something. So that's all I'm going to say about rings and fields. Next time, I'm going to say one more thing about something else, but next time we'll talk about section 19 integral domains. And then I'm just going to bring problems for us to work on. We'll do some together. You can do some in your groups. You can do some homework problems and so on. And we'll, since we're all, well, maybe I'll speak for myself. Since my energy is feeling drained, yours might be as well. And so this might be a good time to just sort of slow down a little bit. All right, so the one thing that I want to say in the remaining 1 minute is a couple of students said this, so I just wanted to clear up a possible misconception during the quiz yesterday. So some of you said that S3 was a subgroup of S4. And there's a way in which that's correct. I mean, philosophically, that's correct. But literally, that's not correct. Because, see, what are elements of S3? Elements of S3, those are functions from the set 1, 2, 3 to the set 1, 2, 3. They're bijective functions. Elements of S4 are functions from the set 1, 2, 3, 4 to the set 1, 2, 3, 4. One of them can't be the other one, right? If I have a function whose domain is 1, 2, 3, it can't be an element of the set of functions whose domain is 1, 2, 3, 4. So they're not, one's not a subset of the other. But if you think about, there's S3 is isomorphic to a subgroup of S4. It's isomorphic to the subgroup of S4 consisting of all the elements of S4 that don't move 4, that send 4 to 4, and then just shuffle up 1 through 3. Okay, so I just wanted to clarify that. All right, that's it for today. Next time, integral domains. I loved integral domains when I was your age. I don't know why, but I'm about to find out again. Okay. Right.
Thank you.
Mhm.
Thank
Bye.
you.
I'll see you next
Thank
time.
you.
You.